Now we continue a little bit with the primary aerosols that actually are shown in this animation that you see from June 2019 and July, and you see basically here three types of aerosol. The orange shades are mineral dust or desert dust, the blue shades are sea salt, and the gray shades are biomass burning aerosols. And you see them coming from different sources and events. In that period, it was mostly the wildfires in the Siberia, and you see this dense cloud around also the Arctic area. And today you will basically learn how to do such simulations. And to do that, I will show you how do we treat the mineral dust emissions, sea salt emission, and biomass burning emissions in ICON-ART. There is another type of natural aerosol, two actually. One is pollen, and the other one is volcanic eruptions or volcanic ash. We don't cover them here, but there are examples of this on our website of ICON-ART that you can follow and learn about. So the main mechanisms of dust emission are basically simple to understand. And if you have a dust field in front of you, you have a lot of dust somewhere, you can emit it in few ways. You can blow it up by blowing on this. So it's the wind, this aerodynamic entrainment directly driven by the wind, very fine particles. But if you also run on the surface, your foot generates particles, this impact. And this is similar to something that we call saltation bombardment. This is when the larger particles impact the surface and mobilize the finer particles. And then we have also the case if these larger particles are aggregates of finer particles, they can also break and emit finer particles, which are then suspended and lofted to the air. How long does the particle stay in the air? Well, these are actually the time scales are very similar in all of them. So these grain sands are really going up for a few centimeters and impact fast. So we are talking about seconds and not minutes or days. Well, for the aggregation, it could be a bit longer, but not really going to much larger scale. So they are very much comparable. One aspect is that the main contribution is usually the saltation bombardment, and this is why we focus on this as the main emission mechanism. There might be cases where other processes also matter, but it's shown in many experimental setups that the saltation bombardment is the dominant process, and this is what we use in the ICON-ART. And what we do for the saltation bombardment, we need to look at the process and the data that we need for that. If you start from the left-hand side, this comes from the metrology. We get the friction velocity, U star, and then we also have the soil moisture and the roughness. And based on the soil moisture and roughness, we calculate something called threshold friction velocity, how much force you need to mobilize the dust particles. This is this threshold. And if we violate this threshold value with the U star, which is actually coming from ICON, then we have the saltation flux calculation, which takes into account the soil particle size distribution and then converts it to dust emission and passes it to the atmospheric transport passes. Let's say the blue part, the yellow part is in the ART, and the rest is basically in or from ICON. And what we need as input in this case is basically the friction velocity, soil moisture, and vegetation cover. Then we have the soil type and particle size distribution. And as the output, we get the dust emission and sometimes the information on some diagnostics like threshold friction velocity, because you want to know which source areas are contributing most to your emission. And by log normal, distribution. I mean this here, you see the number on the y-axis and the particle diameter in micron on the x-axis, and you see three modes with 640 nanometer, then 3.45 and 8.67 micron. These are the three modes that we called A, B, and C for our standard applications, and this is what is also done in the dust forecast system at the DWT. And how does this happen? Just show you a few key reactions. What you see on the top is basically the U star threshold, which is basically tries to uses some empirical parameters, and then once it's calculated, then it goes to this equation, which gives us the horizontal flux of saltation here, and then we convert it basically to the saltation flux and integrate it over the size distribution, as you see in the lower part for the and this is what is really going into the model. And as you see in this, we have a lot of empirical parameters and assumptions, but this has been shown to be a very robust method. Although what you see here, this C at the beginning of this equation here is a tuning parameter. So like everything else that we have to somehow tune, we usually tune this based on the evaluations that we have regularly and try to get the right, at least aerosol optical depth in based on the satellite and observation data. And one of the interesting things that I don't have it here, but I can tell you this, if on the WMO dust forecast platform, which is on the Barcelona website, you can look at the evaluation of different models compared to MODIS and Aeronet network. And IconArt is actually after the UK Met Office forecast, the top forecast in Europe. Although we do not assimilate the AOD, we still are better than CAM's AOD forecast, and it's compared to Aeronet and MODIS. And so I think this system as a whole works quite nice. Let's come to the sea salt. This is another story. Here, we don't need any external files or external parameters. Here, we rely basically on the temperature and the wind of the ocean. And the sea spray is mostly NaCl, the sea salt that we also use in the cooking. And it also contains some anions and cations that you see here. And the map shows you annual global sea salt emission simulated with IconArt. And this also in terms of distribution and total fluxes agrees very well with the multimodal studies that exist. About the processes, we usually have three processes. The first one is related to the air bubbles that resurface. As you see on the top, the air bubbles rise to the surface, and when they burst, they release very small particles or the film drops. So this is the finest or the smallest particles that you can get from the sea salt. But because of this depressurization that we have, we get this jet on the bottom, if I can manage here, and this jet also releases some drops. And this is the second class of, or second size mode of the sea salt. And then we have also, when we have very high wind speeds, we have spume generation, which is basically these larger drops, mainly driven by the wind. So these are the main mechanisms that we have as key parameters contributing to sea salt. There are several parameterizations that try to resolve each of these processes, let's say these three types of modes with different validity range. So they really work for certain particle sizes and certain conditions. Recently, there is a new parameterization, which is a more engineered parameterization, which uses this assumption. So we have again three modes for dust, for sea salt. One is the smallest one, Associated with the film is 100 nanometer, and then we have 3 micron in the jet and the 30 micron spume generation. So you can imagine the 30 is very large. And so we call it the giant mode. And then we have also 3 species in the ICON ARC considered. And we calculate at each grid point over water and at each time step. And the equation looks like this. Sorry, this looks a bit too long, but it's a very simple equation, and it is really engineered one. What you see here, the emission flux is a function of the particle diameter, 10-meter wind speed, and the temperature, empirical parameter based on the sea surface temperature. And you see here for different parameters, it's calculated. If you like, we can say each of these are dominant for certain sizes, each of these 3 terms, and it is somehow representing again this fine to coarse or to giant sizes. But in this equation, temperature is not physics-based, it's more kind of tuning-based, because they wanted to have reasonable emissions at the tropics compared to the subtropics, and they only could do it when they had this empirical parameterization of the temperature. In the other, we have another parameterization in ICON ARC, which basically looks at the temperature and void cap from physical perspective. We don't use that one today, we use this one. And so this is why I'm showing you this example, but this is also documented in our papers, and you can have a look at it. And finally, let's think about the biomass burning aerosols. Here you see one example, the biomass burning events in Canada in June 2023, almost 2 years ago. And you might remember the air pollution in New York and the US. You see the plume now hitting the east coast of the United States, very high concentrations. You see here the AOD, but it also reached the surface in very high concentration. And you had, perhaps in the news, saw these hazy skies of the east coast of the United States. The key parameters that control the biomass burning aerosols or emissions are the fuel availability and type, weather conditions, and topography. The second 2, weather conditions and topography, well, that is kind of simple to get. Fuel availability and type is a very complex business. And it's basically the most of the effort of people who are looking at the fire emissions goes in that direction. Because it depends how much moisture you have, how much dead leaves you have, and what kind of vegetation. You can imagine a fire in Amazon is very different from a fire what we see in Canada or what we see in Siberia. The type of vegetation is quite different from what we see in Australia. And so you cannot apply the same assumptions everywhere. What we rely on is the satellite retrieval. In this case, we just look at the daily mean of the emissions from the satellite data. And we, in ICON ARC, we use one mode to represent the biomass burning with 150 nanometer diameter and the standard deviation of 2. Again, this is up to you. You can have a couple of modes depending on your question that you want to answer. But this is the standard configuration that we test and rely on in many applications. How do we do this? When you want to look at the emission rate, you need to have several things. First of all, you need to have the mass of the emission flux. It comes from the GFAS data, which gives you the emission flux at the points that the fire burns. And this is already, the GFAS is the Global Fire Assimilation System, and it gives you daily the vegetation fire emissions. Then we have the diurnal cycle. I just start from the other. Well, you can imagine that during the day, the fire activity is much higher compared to the night, typically because we have a higher mixing and higher winds during the day than the night. But you can immediately think about situations where the winds are higher overnight. like these extreme fires we had in Australia or in Los Angeles last year. So it was a bit challenges this perspective of the diurnal cycle, but this is a common method to do it because a GFAST gives you the daily mean and you just distribute it between day and night based on this diurnal cycle. And then an important aspect is the plume rise, because it's very critical where your plume ends or where the peak of the plume is. If you look at this shape here, this is what we use in IconArt for our plume rise model. And you can imagine that the wind, the intensity and direction changes with the height. So if you emit at the wrong height, the plume doesn't end in Hamburg, it ends in Karlsruhe. So you totally missed the right direction of transport. So it's very critical to have the right emission profile. And the other aspect is that you can imagine if a plume makes it to the troposphere or stratosphere, the lifetime and the impacts are totally different. A tropospheric plume affects weather, precipitation, and cloud a bit, and it's removed within a few days. Stratospheric plumes remain there for weeks to months and have even climate effects. So this is very important to have the right emission heights for the wildfires. And with this, I hand over to Julia. If first you have any questions, because now you will really go through how do we do this in the model and how we do it in the XML files and how we set up the experiment and start it. But if you have any question about the theory, it is now time to ask. But I'm also here in the room if there's any questions after.
Yeah, on the plume height. So that's dynamic in a model with different parameters to determine the plume distribution.
Yes, we use the one-dimensional model of Freitas in the model, and it is actually, it looks at the environmental conditions and the fire properties and calculates the plume height. Yes, it's driven by, but there is a general tendency of underestimating certain types of plumes. For instance, it's not so helpful in the Pyro-CB plumes, and we also modify the parameterization to take into account for those limitations in some cases.
I have one question before, I want to follow up on that. So that is the only scheme that is available in IconArt, for plume rise.
The plume rise is only Freitas at the moment, yes.
Now moving on to my question. This is practical, not theoretical.
Well, you can always have a fixed height. If you, this is always possible. If you know where your plume exactly is, you can always have an elevated point source and run it. But if you want to have it dynamically, it is only the Freitas model.
You can also probably introduce a profile if you want.
Exactly.
So moving on to my question. What kind of spatial scales are we talking about here? So at which resolutions those parameterizations work, and at which resolutions would they break, would you say?
They never break, they go wrong. Yeah, so the thing is, well, in the convection resolving simulation, it doesn't make sense to use it because the plume rise model is effectively a convection parameterization. And what we do there, we actually simulate the plume rise directly by considering the heat release from the fire and the moisture release. So when we talk about the resolutions, let's say smaller than 3 kilometers, like we have simulation with 600-meter resolution, and there we get the plume heights quite satisfactory without the plume rise model. With the plume rise model, when you go towards, let's say globally 80 kilometers, let's start from 5 kilometers, 13, 20, 40, and 80 kilometers. When you go to higher resolution, the fire radiative power or this surface heat source intensity is distributed in your cell. So the plume rise model does not get enough energy to push it up. And this is particularly the case in the pyroconvective, pyro-CBs, the very extreme cases. In those cases, we have a tuning or we have a scaling parameter that we compensate this for this smoothing of the heat sources. And there's a paper which comes out soon that we account for that and scale it up so that we get the right heights. Like, let's say making this plume rise model scale aware or something like that. So this is and we play around there with the heat release at the ground.
That's an option in the name list that you have given.
Exactly. It is a name. It will be in the October release of the code. It's not yet there in the open source, but in October it will release. And as I said, the paper should be out soon.
And about the emission models that you use, for example, for the mineral dust and for sea salt, are they also working still if you go to kilometer scale resolutions? Or because there you have, for example, if you start resolving topography of the dunes in Sahara, that might change, I imagine.
Definitely. Well, we had one study that we went from globally 20 kilometers down to 2.5 kilometers, and we saw that especially if you are doing with the fronts and the Hadoop systems, you really need to go to the high resolutions. And then what we used there is the tuning factor that I showed at the moment. So we try to adjust it based on the observation. But you're absolutely right. If we go, for instance, now in NextGEMS, there is a group, Martino Close's group at our institute, who is working on mineral dust. And then when they go to very high resolution, they see elevated mass, and then they have to modify the parameterization so they make it more realistic. This application or this parameterization works again very good if you're not resolving convection. But as soon as you go higher to the convection resolving scales, then you have to think about making it more realistic. But beyond that, it works perfectly fine.
Thank you. There's another question with you.
Ah.
You have the time to take it?
Yeah, sure.
We use high latitude sources of dust. In some models, these sources are limited up to 50 degrees north. Would be a significant source of course aerosol in the Arctic?
Very good question, and no, we don't consider it yet. It is one of those things on my list forever, but if we have anyone who can do that, definitely. But this is a little bit the challenge, because the high latitude dust is mostly, let's say, volcanic deposits. And this is, we have to extend the existing data set to consider that. But I know that there was a very big project on this, and perhaps we can exploit the data sets that they developed there. Daniel? Exactly. Yeah, this is, should I repeat the question? I don't know. I didn't do any of the questions, so I just answered. Sorry, online people. This is one of the things that we want to do in the Hertz project, Icon Smart. We compare the seamless configuration with ART. And we actually now defining a master thesis to exactly do that. So that we exploit the Whitecap parameterization, which exists now in the ocean model, and connect it with the other parameterization of CSAR that I mentioned, and the wave model. So both of them, because wave and Whitecap are both of them contribute to the sea salt emission. The problem that we have is that so far the emission parameterizations are usually based on empirical relations, and they just connect, for instance, the 10-meter wind to the wave model somehow. Doing this explicitly is a very interesting thing, so make things more physically relevant. But yes, we are working on it.
Following on this, I'm sorry, I'm just curious because I'm not working with this, but how do you do this for the operational forecast? So we don't have like a dynamic option in this dynamic ocean. This forecast.
We don't do dust. We don't do sea salt in the operation.
Okay.
So we only do dust.
But if you would do it, then at the moment you're saying that you cannot use dynamic ocean and
Yeah. Well, even if you use the dynamic ocean, you can still use the simple parameterization that I just showed here, which only needs the sea surface temperature.
Yeah, but it doesn't see it.
So it doesn't see the wave and white cap from the ocean. Yeah. It really doesn't benefit from coupled ocean. That's it. Yeah. Okay, if there are no further questions, then Julia, the stage is yours.
Yeah, so hi everyone, also from my side. I want to guide you through the experiments today. So first of all, the primary aerosols, and later on in the afternoon, also the secondary aerosols. For the primary aerosols, we want to look at aerosol tracers and modes and want to introduce online emissions, in this case for mineral dust, sea salt and soot emissions. And for this first experiment, we mainly need three most important XMLs are the one for the emission, the modes and the tracers. And I want to give you a brief overview for these three XML files so that you later on know what to do in the experiments. So first of all, coming to the aerosol emission XML, this is a short part of it. Here, an example for dust. So, for example, here you have three dust modes for the emission, which means that you would need the emission median diameter for the 0th and 3rd moment and the standard deviation to define the log normal distribution. Here it's only written for the first mode, but because you said you have n mode equal to 3, you would have to repeat it 3 times so that every mode is defined. Then also the modes XML is important. So this is where you define the modes that are then later on transported. So this here is an example for the insoluble accumulation mode. Again, you define the median diameter and the standard deviation for this mode, but also this is less important for today. You can also choose the optical properties for the mode, which are then linked to another file in the CART optical property.
Will you jump into it because I just noticed? Do you remember the modes of variability of aerosol that I showed you? Composition, size distribution, mixing state, and morphology. This insoluble accumulation tells already the mixing state and the size. The first tag that you see on the mode. And the species is dust A. So in this part that you see now, we have all of these three information. And the model knows that it has to treat dust as an insoluble particle in the accumulation mode. And you can extend it 9 times for dust. We don't do that because it's unphysical, but I just wanted to bring it back to the these modes of variability that I showed you. And the morphology is in this lookup table, optics. You can use here the dust A is the lookup table has a non-spherical dust, but you can also choose the option spherical, and then you have all modes of variability of the aerosol. Sorry.
No problem. Thank you. Yeah, so this is the modes XML, and then the other important XML for today is the aerosol tracer XML. So again, this is an example for dust. So what you could see is that dust exists in this case in the insoluble accumulation mode and insoluble coarse mode. So in that way, you link the tracer to the modes. Then you have some additional tag for, like, for example, the density, the mole weight, or also this soluble tag. That is here again less important because we only have insoluble particles, but for the afternoon we will also look at mixed and soluble particles, and there this tag is becoming more interesting. Yeah. So far on the XML files, what you should do now is that you copy the notebook that is given here in this link. To get all the ICANN-ART experiments. So when you execute the cells in this notebook, you will copy all experiments for today. So the primary, the secondary aerosols, and also the air quality. And then you would go to the folder for the primary aerosols and find a Jupyter notebook there, which is, I think, called primary aerosols. And there are further instructions what you will have to do.